Among the different methods, sterilization by gamma rays requires the use of a radionuclide. One of the most used radionuclides is cobalt-60. It has a half-life of about 5 years and decays into nickel-60 that immediately emits two gammas of about 1.2 and 1.4 MeV. The production process of cobalt-60 is based on a nuclear reaction induced by neutrons. It consists of neutron irradiation of the target made of cobalt-59 for a specific irradiation time and the subsequent encapsulation of the irradiated pellets. The irradiation of the target usually takes several months. All over the world, there are more than 160 irradiators processing over 260 million cubic meters of product every year. Cesium-137 is also used as gamma source, but its penetration property is lower than cobalt-60. Cesium-137 has a half-life of 30 years and decays by beta emission to metastable barium-137, that in turn decays to ground state by emission of gamma rays of 0.66 MeV. Like other beta-emitting sealed sources, Cesium-137 is produced by nuclear fission in nuclear reactors, and it is embedded as cesium chloride into glass beads contained into sealed metal capsules. The radionuclides has to be prepared as a sealed radiation source. This means that it is contained in a capsule that prevents environmental dispersion and enables its safe handling. Sealed radioactive sources are produced by placing reactor-irradiated metal pellets or cylinders into capsules sealed by welding. Such capsules, also called pencils, are generally made of an inert and radiation-resistant metal, like steel, platinum or titanium. The overall activity of the source can be controlled by assembling an appropriate number of pellets. The overall activity of such a gamma source could be extremely high, even in the range of terabecquerel. Quality controls are performed after the production of sealed radioactive sources in order to check the activity, surface contamination and leakage. The radioactive isotope processing facility has to consider the radiation protection issues of workers and also avoid radioactive contamination of the source. Environmental and personal dosimeters are used to assure the safety of workers. Gamma radiation requires absorbing shielding walls made of high-density materials, like heavy concrete or lead. Sources are manipulated with the use of hot cells, separated from their surrounding by shielded walls and equipped with manipulators. Hot cells provide protection against external irradiation and radioactive contamination of the surrounding area. Moreover, several air filter systems are present to prevent possible radioactive leakage to the environment. We have discussed the production process of the radioactive sources. Let's go on to discover the sterilization facility where they are employed. Products arrive on a truck and they are unloaded at the processing facility. Operators set the scheduling, processing, certification and release of each product. Products are loaded into the processing containers. Dosimeters are placed to check the absorbed dose. The containers are transported by an automatic transport system inside the irradiation room where they are exposed to the radiation field. Two possible irradiation configurations could be adopted in a plant. For continuous irradiation, the product containers are moved around the radiation source on a conveyor belt that passes through the maze. For stationary irradiation, the radiation source is moved into the irradiation room around the product containers. To shield the surrounding of the irradiation room and to maintain the radiation level close to the natural background, the radiation source has to be attenuated by a suitable shielding. It generally consists in concrete walls, normally 2 meters thick, constructed as a maze to avoid secondary radiation leakage. The activity of a cobalt-60 source can vary from tens kilocurie to several megacurie. The dose ray is directly related to the installed activity of the source. The operator sets the radiation dose delivered to the product by adjusting the exposure time, the distance from source, or the conveyor speed. Dosimeters irradiated together with products are analyzed to confirm that the planned dose has been delivered. All documentation and processing history records are registered according to a certified quality system, and if customer specifications are met, the products are released. In gamma irradiators, emission of gamma rays from the source cannot be stopped, so to stop irradiation, the source needs to be moved away. The source can be placed into a pit for dry storage. Otherwise, the source can be stored in a pool for wet storage by exploiting water as additional radiation shielding. Of course, due to the decay, the strength of the radioactivity level of the source decreases with time, about 12% in 1 year and halves in about 5 years. Therefore, operators have to take into account such loss of activity by modifying the processing cycles. However, when irradiation time becomes impractically long, source replenishment is required. Additional pences of cobalt-60 are added periodically to the source rack to maintain the required capacity of the radiator. At the end of their useful life, typically 20 years, cobalt-60 pences are removed from the radiator. Generally, they are returned to the supplier for reuse, recycling or disposal. In about 50 years, 99.9% of cobalt-60 would decay into non-radioactive nickel.